So to introduce velocity, let me first talk about constant velocity. So imagine that I have a coordinate system. So here's an x-axis, and imagine that every division is equal to 1 meter, and that the particle is executing motion as I'm about to describe here. So for this first example, let's say that in the first second the particle has a displacement of 2 meters in the positive x direction. So I should highlight that that's the positive direction. And then in the second 2 seconds it does the same thing. And then again and again, etc. So the velocity here is the displacement divided by the time it takes to make that displacement. So this is the general thing to remember here about velocity is velocity is equal to the displacement over the change in time taken. We'll just say that. And so I'm going to introduce a notation called the delta notation here, which we can write the displacement as the change in position, since I'm using x to track that. This is going to represent the later x minus the earlier x divided by the time taken. And I don't really have to put a vector sign on top of here, since it's a 1D problem, and a plus is going to tell me the direction I'm going, or minus is going to tell me the direction I'm going. In this case, I'm going in the plus direction. So let's do a couple of things here before I go on and show you another example of constant velocity. First of all, let's make a little table here of this, and I'm going to do that over here on the side. I'm going to say time in seconds and position in meters. At time 0, I'm at position 0, x equals 0. At time 1, I'm at position plus 2. That would be right there. At time 2, I'm at position plus 4. At time 3, I'm at position plus 6, etc. So if I were to plot this in terms of the position versus the time, I would get something that looks like this. So this is x in meters versus time in seconds, and I'm going to get something that looks like this. I'll plot it in red here. Okay, so this equation, the equation for this straight line, which goes through the origin and starts at 0, is x as a function of time is equal to 2t. You can see that that's true by looking over at this table here. So let's do a different plot now, and this second plot is going to be a plot of the velocity as a function of time. So here's this is velocity, which is in meters per second, and this is time, which is in seconds, and I'll make this a different color plot. Let's say I make that blue. And so the velocity for this motion is plus 2, because in each second it's making a displacement of plus 2 meters. And so the velocity would be a constant flat line plotted like this. Okay, so that's the first example. Okay, second example, same axis as we have above, just like this. I'll redraw the x-axis. Same positive direction here, but in this second example, the particle motion is given as 2 meters to the left in 1 second, and again 2 meters to the left in 1 second, and again 2 meters to the left in 1 second, like that. And so for this particular example, if I make an analogous table, time in seconds and x in meters, the table will look like this. At time 0, I'm at position 0. At time 1, I'm at position -2. At time 2, I'm at position -4. Time 3, -6, etc. And so where the velocity up here was 2 meters per second, the velocity down here for this second example is -2 meters per second. The x versus t would look like this. So here's my x versus time in seconds. It's going to look like this. It's going to have an equation, x of t is equal to -2t, and the v versus t for this one is going to look like velocity in meters per second versus time in seconds is going to be, again, a flat curve, but now it's going to be at -2 meters per second. Okay. So both of these are examples of constant velocity. For this one, the velocity is positive because the particle, the object, is going in the positive x direction with the same displacement and the same time interval. And the second example is constant velocity in the negative direction.